Hello, thank you very much for tuning in to watch my talk. I'm going to speak to you about barium tagging for the next neutrinoless double beta decay program. So NEXT is a program of high-pressure xenon gas time projection chambers focused on achieving a large, very low background xenon neutrinoless double beta decay surge. Following two prototype phases, NEXT embarked upon two demonstrator phases. There's a NEXT White and NEXT 100. The one is running, the other one is under construction, both at the Canfranc laboratory in Spain, and these will be covered in another TAUP contribution by my collaborator Alberto Usom. And these two demonstrator phases are anticipated to be followed by two physics class phases called, first of all, NEXT HD, which is a ton scale high pressure xenon gas detector without barium tagging. An expression of interest for NEXT HD is in preparation for the LSC laboratory now, and there is a sensitivity paper available on arXiv, which has just been accepted by JHEP. And this would be followed by barium tagging phases, which would incorporate the technologies to be discussed in this talk. Now, the sensitivity of NEXT HD is calculated under varying assumptions. We can consider different background models. In particular, there are two models shown on this plot. The first one assumes the use of materials which have been assayed for the NEXT 100 program in the red. We can see some modest sensitivity improvement if we incorporate here materials which are cleaner and have been found by other collaborations, but not previously used in NEXT. That's shown in the blue line. And if we further enhance the detector with a gas mixture which reduces diffusion, then we can slightly improve the topological signature, and that would give a model like the one in purple. You see the sensitivity doesn't vary very dramatically depending on the precise assumptions. However, the addition of barium tagging, the subject of this talk, could dramatically improve sensitivity, both because it would greatly reduce experimental backgrounds to a near negligible level and could increase efficiency in principle. And so to see the sensitivity of the barium tagging curve, I have to shift the axes. So here is the sort of optimistic projection. Now, the idea of barium tagging is to use the fact that in a double beta decay event, xenon steps two steps along the periodic table, leading to barium. And this is not something that any of the non-double beta decay backgrounds, which are mostly from gamma rays, can do. And so if you could identify the appearance of this barium ion and also include a approximately 1% full width half max energy resolution to tell the difference between two neutrino and neutrinoless double beta decays, you could in principle achieve a background-free experiment. So this concept is not new. It was first introduced by Mo 30 years ago. But the question is a technological one. Is it possible to develop methods for extracting and imaging single barium ions or atoms in ton-scale volumes of xenon? So one question you have to address here is, what kind of barium object are you looking for? And the answer is different depending on whether you're talking about a liquid xenon environment or a gaseous xenon environment. Now, in dense media, after a double beta decay event, there is a cloud of electrons surrounding the ion, and those electrons recombine onto the ions. They fall back onto the positive charges and cause partial neutralization. And this is a strong enough effect that in liquid xenon, the barium daughters are expected to be distributed between being atomic and being singly charged ions. Now, in xenon gas, there is very little recombination. And that lack of recombination means that the daughter ion is expected to stay charged. In fact, it's double charged. Barium 2+ is where it's energetically favorable for it to land. And actually, this idea has actually been tested with experimental data. In particular, in the radon decay chain, there's various alpha and beta decays. And by looking at where the daughter products of this decay chain land, whether they land on the cathode and then decay there or decay in the volume, you can establish the charge fraction. And you see that indeed, in gas, the beta decay products stay very completely charged, whereas the beta decay products in liquid xenon undergo partial neutralization through recombination. But so, okay, we're looking for a 2+ ion. And that actually introduces additional challenges relative to looking for a 1+ ion or a neutral atom, because a barium 2+ ion has an atomic structure which is a noble-like core with no low-lying outer electrons. And that means it has no fluorescent transitions you can use for atomic fluorescence measurements very easily. So you have to add fluorescence transitions yourself somehow. And the way we're trying to do this is a concept that was brought into the double beta decay arena by our co-spokesperson, Dave Nygren. And that's to use single molecule fluorescent imaging. Now, single molecule fluorescent imaging is an ion identification method which has been developed in chemistry and biochemistry for imaging calcium 2+ primarily. It's an important signaling ion in neurons. And the way this works is you take a molecule which is designed to be non-fluorescent until it captures this ion, and then it becomes fluorescent. And effectively, the way these molecules work is they have two components: a receptor, which here is a bunch of carboxylic acid groups, these CO2Hs at the top, bonded to a dye, and the dye here is fluorescein. So left to its own devices, this dye would just be fluorescent. But what happens in this molecule on the left is that when you excite the dye, a lone pair of electrons on this nitrogen jump into the unoccupied orbitals, and they quench effectively the fluorescence. Now, when this captures an ion, the situation is different, because now there's a positive charge trapped in this cage, and that pulls the electrons on this nitrogen switch atom into a kind of bonding configuration, and that means that stops the quenching of the dye. And so this then goes from non-fluorescent to fluorescent upon capture of an ion. And this is an example, very famous molecule from biochemistry called fluo3, which is designed for sensing calcium. And because calcium and barium are chemically similar, they're above one another on the periodic table, the idea is that these dyes, which are developed for calcium, can be used for sensing barium. So this kicked off an R&D program to check whether this is the case. And so the first paper is shown at the top here. This was a demonstration using these commercial compounds, fluo3 and another one called fluo4, to prove that indeed these compounds, which are sensitive to calcium, can sense barium. And then that was relatively quickly followed with an experimental demonstration that not only are these sensitive to barium, but they can be sensitive to barium at the single ion level. So this figure at the bottom shows on the right here is a single barium ion identified using these fluorescent molecules. And the way you know it's a single ion is if you look at the time dependence of the fluorescence here, you see it's shining brightly, and then at some point it undergoes a discrete step to zero fluorescence. And that's called a photobleaching reaction. That happens when the molecule, which is in this excited fluorescent state frequently and is chemically reactive, undergoes some destructive chemical reaction that stops it being fluorescent anymore. And the fact that it goes in one step rather than decaying gradually means that you know it's a single quantum emitter rather than many clustered together, gradually decaying away in fluorescence. So that was one of our first images. This is our more modern version of the images we take of single barium ions now. Hopefully this video will come out looking okay on YouTube. But here you see a field of blue dots, effectively. This is sped up by a factor of, I think, 3 or 4 compared to real time. And you see these dots, each one at a time, flickering out of existence. And each one of those is one barium ion detected and undergoing a photobleaching process. Okay, so after that demonstration, there was a lot of optimism that this would be something we can implement in a xenon gas detector, but it quickly became clear that these commercial compounds are actually not useful for operation in the dry environment of a time projection chamber. And the reason is essentially twofold. So these molecules are made of a receptor coupled to a dye, and this particular choice of receptor, the carboxylic acid-based receptor, has to deprotonate those hydrogens. They have to fall off in order for this to bind an ion. And that actually is something that requires the stabilization of a solvent in order for that to happen. So this won't work in a dry environment. They'll stay stuck on and it won't be sensitive to ions. Secondly, the dye, fluorescein, is a dye that actually has to undergo a conformational change as part of its fluorescent process. And that's also inhibited in dry environments. So neither the receptor nor the sensor nor the dye here will work in dry environments. And so novel custom chemosensors are required for barium tagging. So in response to this, we initiated an R&D program to invent new custom chemosensors with dry phase performance. So the left shows the old version, the fluo3, the biochemistry inspired sensor. On the right, you see the first generation of ones we created, and these are based on crown ether receptors. So now the barium ion binds into this crown by essentially binding with the electron density on these oxygen atoms, or chelating. And this chelation, critically, doesn't require anything to deprotonate, so it should work in the dry phase. This then essentially brings these nitrogen lone pair, again, electrons into a bonding configuration that suppresses fluorescence quenching. And the dye molecule is a rigid aromatic in this case. So in this left one, it's anthracene. In the right one, it's a dye called naphthalamide. And these are both really rigid molecules that don't bend around in the fluorescent process. And so this was designed then in order to solve these problems of dry sensing. So I should also mention that these molecular designs have been optimized computationally using density functional theory. One of the things that's particularly important for barium tagging dyes is that we have not just sensitivity, but selectivity, because in every solvent, there's a huge amount of stray calcium ions and all kinds of other metal ions. And in order for the sensor not to be swamped at the single ion level, it needs to be very selective for barium. So we had to design sensors that were deliberately insensitive to the other metals in the periodic table, but sensitive to barium. Anyway, these molecules were then synthesized by our collaborating organic chemists, and dry single barium dication sensitivity was demonstrated with these molecules. So here you see on the right an image of an individual barium ion, which has been sensed without any solvent now in a dry environment. In parallel, there's been another direction of R&D to make a different kind of sensor. So the sensors that we've been developing at UTA have always been based on switch on. So they're off, they have no fluorescence, and then they suddenly step up in their fluorescent intensity when they capture an ion. At DIPC in Spain, they've been working on color shift based approaches. So here you have a molecule which is already fluorescent before it's bound to barium. And then it captures barium, and not only does it engage with this lone pair on the switch nitrogen, but it also interacts with a nitrogen on the fluorescent group, and that causes the fluorescence to change color. And they probe this with 2-photon microscopy, and this change from green to blue is what is the telltale sign of capturing a barium ion. So this is an interesting different direction that's also being explored. The bicolor sensors have also been exposed to barium perchlorate molecules in vacuum. And so essentially barium perchlorate is a fairly loosely bound barium salt. This is evaporated from a Knudsen cell and exposed to the pellets of this fluorescent molecule. And what happens is then there's an in vacuo chemical reaction where the barium perchlorate binds up with the sensor in this complex, which produces a final state which sort of resembles what you would expect to see in the xenon gas system, where there would just be a bare barium, but stuck to these two chlorine counter ions, or perchlorate counter ions here. This is simulated final state with a density functional theory. So indeed, they see then when we evaporate the barium perchlorate into the sensors, the fluorescence changes from the green to blue as expected. And actually, the 3D structure here is now being confirmed by a scanning tunneling microscopy to see if it really looks like this. And that's interesting work, which hopefully will be coming out soon. So, but the important thing here is that in vacuo barium complexation reactions are shown to proceed with crown ethers with this technique. So eventually, this needs to be done with a single molecule microscopy, which is implemented over a reasonably sized surface area, maybe millimeter squared to centimeter squared, inside a high pressure gas environment. So this is the prototype device which has been constructed, which is a 3-stage microscope with a custom made objective for high pressure use on a high pressure viewport. And this has now been used to scan millimeter squared surface areas in 10 bar of xenon gas with single ion sensitivity. So this is the first microscope of its kind and a prototype for the sensors that we will use in the barium tagging experiment. So this image on the right is a very preliminary image. Here you have a 1 millimeter by 1 millimeter scan area, and each one of these little squares is one frame taken with the microscope as it's scanning around. And if you zoom in on one of them, say this one, you see a field of background and then one bright spot, and that one bright spot can be associated with being a single barium ion and then watched until it photobleaches in a discrete single step. And so this demonstrates the single ion sensitivity over a 1 millimeter squared scan area inside a high pressure environment. So as you see, these sensors are becoming quite mature. There's iterative R&D, both on the chemicals, the sensors, the microscopes ongoing. But what is really needed is a demonstrator now, which will show this working in response to double beta decay. There's various demonstrator concepts under development. 2 I want to mention in particular are the next BTX concept. In this concept, which is being led by Spain and Israel groups in the collaboration, the ion would land on a completely sensitive coated cathode, and then a sensor would be actuated to where the molecule is. The concept that we're pursuing in the US is called Next Crab. In this demonstrator, the idea is that the barium 2+ ion is brought by RF carpet concentrator methods to a small number of sensors which resemble the one I showed on the previous slide that scan over millimeter squared to centimeter squared surface areas. And these demonstrator phases are under intensive development now and hope to be operational at this point on something like a 2 to 3 year timescale. So here's my summary slide. I have probably run out of time, so I don't think I'll read every bullet point, except to say that barium tagging is a potentially transformative technique which would dramatically enhance sensitivity of xenon experiments for neutrinoless double beta decay, and there is rapid and exciting progress on this technology constantly ongoing. Thank you very much for your attention, and I hope you enjoy the rest of the conference.